Good day, everyone. Good morning, good evening, good afternoon, and where you're located. My name is Artem Yarovinsky. I'm Chief Business Development Officer of Velta Holding. It's a pleasure to be speaking with you all today as a part of the REPTiS project. Today's webinar is mining and beneficiation of ilmenite-bearing heavy mineral sand, and I'll be providing an overview of the ilmenite-bearing heavy minerals industry. We'll cover the market drivers, the geological context of this commodity, and then I will present a short case study on an operational optimization project. We successfully implemented at our own titanium Birzulivske mine in Ukraine. This overview will be more high level, I suppose, for those who are from the industry. But so those who are just interested in this industry, I suppose it will be very detailed in this context. So in both ways, you will receive probably some insights and some useful information. So starting, titanium. So to begin, why titanium? As mining professionals, we know that the why is all about the properties of the markets. Geologically, it's not the rare material. Titanium is ninth most abundant element. But the challenge is, as with many metals, in finding its economic concentration. Its value is driven by its unique material properties in the metal form. You can see the list here, but the key takeaways are its high strength to weight ratio, its extreme corrosion resistance, and its biocompatibility. This combination of properties makes this metal critical or even strategic material, as stated by the European Union. And for us in the upstream, the primary economic minerals we as the industry target are ilmenite and its high-grade sister material, rutile. Going further for industrial upstream, here is the most critical markets dynamic for our commodity, and it's something that surprises many outside of the specific sector. But because when you look at this industrial upstream, the vast majority of all titanium feedstock, we are talking about the 90 to 95% of the global production, does not go to the titanium metal sector. When you are used to, or maybe not used to, but how you imagine the titanium, even looking at your latest iPhones with a titanium casing. But the titanium pigment sector, because it's chemically refined, often through slag or synthetic rutile root intermediates to produce this titanium dioxide. This is a massive 7 million tons, or probably already 7 million tons chemical industry market. The demand for this product is primarily driven by paint, plastics, and paper industries. Basically, everything you see white around you contains titanium dioxide, from papers and sunscreen creams to colors of houses and cars, planes, and going further. The high-tech aerospace and medical applications, if everyone thought of, that is the metal sector. It's much smaller market by volume, I mean around 320,000 tons per year, but it is extremely high value and strategically critical market. Going further upstreaming, the slide provides a visual breakdown of those two parallel value chains. On the left, the pigment sector, high volume chemical driven industry dominated by players from western part of the world like Kimur, Stronox, and also Chinese players that are actually entering the Western markets right now. And these Chinese players that I also stated here, according to the latest market information, the biggest one in the world is the Lemon Billions Group. And on the right side, the metal sector, high spec, high cost, specialized metallurgical industry with key players from Japanese companies like Osaka or Toho Titanium, specializing in aerospace applications. And unfortunately, due to the war, the only one European production of titanium sponge was stopped. It was the British titanium magnesium combined located near actually our city in Ukraine. But nevertheless, our job in the upstream is to provide the reliable and consistent feedstock for both these vital and very different industries. Going further to the types of ores, so where do we get this feedstock from? As a slide notes, over 80% of titanium minerals are extracted from coastal or alluvial deposits. So unlike many commodities, we are not, for the most part, our hard rock industry. We are heavy mineral sand industry. These deposits are the result of millions of years of natural geological concentration, where erosion and hydraulic action separates minerals by the specific gravity. Our primary target is ilmenite. It's the workhorse of the industry. As you see at the top photo, it's the most common source, accounting for about 90% of all of the feedstocks. Alongside, you see the rutile. Rutile is high-grade and high-purity feedstock, naturally containing up to 95% of titanium dioxide. It's a lower volume, higher priced co-product that adds significant value to any deposit if there is. To complete the mineralogical picture, there are two other sources. Leoben is not a distinct mineral, but rather an alteration product of ilmenite. It's found in the same deposit. It's simply ilmenite that has undergone natural weathering, which leaches out iron and relatively increases the TO2 concentration. Titan ferrous magnetite is a different category entirely. This is an iron ore mined by steel producers where titanium is presented within the magnetite lattice. The titanium is then recovered as a co-product or byproduct from the slag during the steelmaking process. It's an important alternative feedstock, but it's tied to the iron and steel industry. Going further for the mining of the ilmenite. The geological difference dictates mining methodologies, which fall into two main camps. Yeah, we'll name it camps. On the left is hard rock mining. This is conventional open pit operations. You drill, blast, load, and haul. The ore is then fed to comminution circuit. It's like crushers and mills to liberate the minerals. This is energy intensive hard rock process. The only one European producer that operates such deposit is Kronos, which is titanium dioxide producer. They have a titania mine located in Norway. And in European Union, it's the only producer of ilmenite, actually. On the right, and the focus of my talk will be the mineral sand mining. Here, the challenge isn't comminution. Nature did it for us. The challenge is bulk material handling and efficient gravity separation. So you could see this here, like photo with an example of such operations. Companies that mine with such technologies are Luca Kenmare, Rio Tinto in Australia, South Africa, or Mozambique. So there are two main methods. First one is dredging, wet mining. So a dredge-fed operation, pumping a slurry directly to a floating or land-based concentration plant. And second one is dry mining, when using conventional mobile fleets like dozers, excavators, and scrapers to move the ore, which is then typically slurried to mining unit for transportation to the plant. Hybrid method. Now I'd like to present our initial operation case study from the Birzulivske deposit, our deposit in the Kirovograd region, Ukraine. We employ a hydromechanical mining method, pretty efficient hybrid system. As you can see from the overview, it's a three-stage process. First stage is excavate. We utilize a large walking drag line, really enormous in size units, proudly built in Ukraine for bulk excavation, side casting the ore sand to a temporary pile. Typically, one such kind of excavator is assigned per the mining phase. Then we liquefy, so the ore is slurried in C2 using high-pressure water cannons, which we call hydromonitors. And the pump, so this creates a high-density pulp, which is fed to a downhole pumping unit and transported hydraulically over long distance directly to the processing plant. This is quite effective system, which can be optimized, of course, that minimizes whole truck usage and associated costs until you go to distant mining points from the facility, beneficiation facility itself, and that is when optimization should came into place. So here is the video. I will try to play it. So to give you a brief idea, here is the process I just outlined. What you're seeing at the first step, the excavation. This massive machine is a walking drag line. Its job is to dig the ore sands from the mining phase and pile them up. You can see how it's mining, excavating, and then here comes the hydro part. So you can see hydro monitors that are blasting the pile where it's piling. Sorry about that. From there, the pulp is fed into a slurry pumping unit, which is powerful enough to send the material immediately to the processing plant. It's all done by hydraulic transport, pushing the slurry through a high-pressure polyethylene pipeline over a distance of 1.5 or 2.5 kilometers. It's a very streamlined and continuous operation. And as you can see, it's dig, liquefy, and pump process. This was our standard for a long time. And here you will see this innovation in action, like I name it. So, however, as many of you will appreciate, any mining system that is directly coupled to a processing plant inherently vulnerable. Yes, and our primary operation bottleneck was lower utilization of the processing plant. We could experience feed interruptions primarily driven by plant downtime required for drag line moves and pump repositioning sequences. To solve this, we implemented a combined transport scheme. The core of the project was to decouple the mining and processing phases. We achieved this by engineering an ROM, which is run-of-mine stockpile, to act as the decoupling buffer. So the new fall is, like, as you see on the slide, excavated hole. So we use a flexible mobile fleet of hydraulic excavators and haul trucks. Then we create a buffer. They deliver the ore to the central ROM stockpile, which is strategically located far closer to the beneficiation facility. Then feeds the plant phase. A dozer manages the stockpiles and provides a consistent homogenized feed to a stationary pump station, which then creates the pulp and feeds the plant. So talking about advantages of this technology, This one change this one change had a cascading positive impact on our entire operation. First, we virtually eliminated mining-related plant stoppages. This has had a positive impact on plant utilization, equipment availability, and stable operations. Secondly, this RAM pad functions as a strategic reserve. This builds operational resilience against unplanned mining downtime, be it weather-related, fleet maintenance, or any other field issues. Third, from an engineering standpoint, moving to a stationary pump in an optimized location allow us to maintain a higher and more consistent, I would say, pulp density. This has direct positive impact on our energy per ton metrics and overall throughput. And finally, these factors gives higher utilization, increased resilience, and better energy efficiency, which translates directly to a reduction in our unit operating costs, and last but not least, carbon footprint overall. So to conclude, this is what I wanted to share actually today with you on the titanium and particularly feedstock mining side. I hope I have covered basics for it and give you some case study ideas for better understanding. I was not sure about the audience that will be attending today. So apologies if the material was not so deep technically, or maybe opposite, not so basic. I'm more than sure that the next speaker, Michael Lechner from University of Leoben, will give much more technical packed information on the beneficiation side of the titanium industry. And by that, I wasn't sure. That said, thank you for your time and hope you see on our next webinars. Thanks.